Okay, now we're going to look at section 2.4 and 2.5 with significant digits, also known as significant figures. They mean the same thing. Uncertainty in measurement. Whenever you have a measurement, you're always going to have a degree of uncertainty in there. So you know what is for sure that you actually measured, and then which part is the uncertain portion. And that's really what this is going to be. When using a measuring device, use the limit of the scale plus one digit beyond. And in a couple of slides, we'll see an example of that. So you go, for instance, if you have a ruler, you go to the markings on the ruler, and then you have to interpolate between the digits after that, so that way you get one more significant digit. So here is the example with the ruler. Here we have our ruler. Here we have a pin that we're measuring. So the certain digits are 2.8. We know that it's between 2.8 and 2.9 centimeters long. But imagine then that in between that 8 and the 9, that you visually are figuring out, well, it's about halfway in between. So the certain digit's 2.8, it's about halfway, so you would report this as 2.85 centimeters long, one digit beyond the scale reading. Now, electronic balances, that last digit usually is bouncing around a little bit, and you kind of have to guess at where that last digit is most of the time, and that is your uncertainty. Rules for finding significant figures. So non-zero integers always count as significant figures. So if it's a non-zero number, it is an integer. The problem is when you have a zero. We have three different types of zeros. We have leading zeros. A leading zero precedes the first integer, like down here we have 0.048. So this has two significant digits. Leading zeros are placeholders, they never count. Captive zeros. Zero is a number, so therefore it does count, it is significant. You measured the tens place, you measured the ones place, you measured the zero, it just happened to be a zero in the tens place, and then the 700ths is your estimate or guesstimate of what that digit would be. Trailing zeros only count if there is a decimal point. Otherwise, they are considered placeholders. So what you want to do is you're looking to see if there's a decimal point. So we have 9.300. So the 9 is significant, the 3 is significant. This 0 and this 0 are also significant. This one you measured, this was your best estimate. It just happened to be right on that line, so you called it 9.300. Whereas 150 only has two significant figures. So again, if there is a decimal point, the trailing zeros will count. If there's no decimal point, the trailing zeros do not count. Exact numbers have unlimited significant figures or significant digits. There are exactly 2.54 centimeters in an inch. That's now the definition of an inch. If you're counting people at a baseball game and you have one of those little hand clickers and you keep clicking it every time somebody comes into the baseball game, that would be an exact number. You can't have a half a person, you can't have 3/4 of a person. You either have a person or you don't have a person. Here is my trick. This slide is not in the other PowerPoints that I loaded. I added this one into it. This is the easiest way to find the number of significant digits. Look for a decimal point. If there's a decimal point, everything including and after the first integer is significant. If there's no decimal, then the number must be greater than 1, because otherwise there'd be a decimal because it represented smaller than 1. And the trailing zeros don't count then. So in 12.0500, there's the decimal point, there's the first integer. Everything including and after the first integer is significant. So we have 6 digits and there are 6 significant figures. Here we have a decimal point, a number smaller than 1. There's the first integer. There's a 0 after it. Trailing zeros count if there's a decimal point. So there's two significant figures here. These leading zeros are placeholders, they don't count. 79,000. No decimal point, therefore the trailing zeros are not significant, and there are 2 significant figures. Whenever you have scientific notation, then only digits that are significant are shown in scientific notation. So 300 written as this way would only have one significant digit. If you wanted to indicate that this 0 is significant, you could either put a decimal there at the end, or put it into scientific notation, which would be 3.00 times 10 to the second power. It's a lot easier to work with significant figures when you're calculating them if they are in scientific notation, because as we'll see in a moment here, there's two different rules for determining how many significant digits your answer should have. When rounding, don't round until the end. And what we're going to do is we're going to do the same type of rounding that you learned in elementary school. You look at the digit you're going to round to. If it's greater than or equal to 5, you round up. If it's less than 5, you round down. Now there's another type of rounding called engineering rounding. We're not going to worry about engineering rounding, but if the number is a 5, you look to see at the preceding number. If it's even, you round up. If it's odd, you round down, with the idea being that half the time you round up, half the time you round down, and the rounding error would cancel each other out. Now the reason you don't want to round until the very end is because you may introduce a rounding error. If each of these points in here you went ahead and you rounded, then there is a good chance your final answer is going to be off simply because of a rounding error. So this just states the exact same thing I just said. You want to carry the extra digits until the end and then you round off. When you have mathematical operations, when multiplying or dividing, your final answer has to have the same number of significant digits as the least number of sig figs in what you are multiplying or dividing by. So in this case, we have 4 sig figs. Here we have 2 sig figs. So the most that our answer can actually have is 2. Otherwise, you're going to be reporting this to a value that is more precise than you actually measured. So 1.342 times 5.5 does give you 7.381, but we have to round that to 2 significant digits. There's 1, there's our second one. Look at the number after it. It's an 8. Last I checked, 8 was bigger than 5, and we get 7.4. When you're adding or subtracting, the rule is a little bit different. It's the least significant place value. Now normally it's a decimal, but it doesn't have to be. It could be say, for instance, if you have 15 plus 10, but there's no decimal at the end of the 10. That 10, if it's not an exact number, it only goes to the tens place. You don't know what the ones place is. It could be anywhere from 8 to 12, somewhere in there. We don't know. So we can't report 15 plus 10 as 25. We would have to report it as 30 if we were adding them in that last significant digit did not have a decimal on there. Which reminds me of a joke. Why was 6 afraid of 7? Because 7 ate 9. Well, why did 8 eat 9? Well, because it heard you're supposed to eat 3 squared a day. Alright, so when using a measuring device then, again, what you want to do is you want to use the limit of the scale and then 1 digit beyond. So here we have a graduated cylinder. Here you can see a very defined meniscus. We always read to the bottom of the meniscus. So in this case, this goes to the nearest 0.2 milliliters. Here's 3, 3.2, 3.4, 3.6, 3.84. So we know that it is more than 2.246, and it's just about up to the 2.8. So I would call that maybe 2.80, possibly 2.79. So we're going to the limit of the scale, 1 digit beyond it. Over on this side, though, this is a 1 milliliter graduated cylinder, and each of these lines is 0.02. So looking closer at it then, we have 0.2, 0.22, 0.24, 0.26, 0.28. So you report this as 0.28 milliliters, the limit of the scale, 1 digit beyond that. So I would say 0.280. Okay, so now what we're going to do is we're going to take our two amounts here and we're going to add them together. So here we have 2.8. Here we have 0.28. So when we add those together then, we're going to report it as 3.1. We can't go more precise than this because this one only goes to the nearest 0.2 milliliters, so a 1 decimal after the milliliter. And the first graduated cylinder is what is limiting the precision of the total volume.